Adrian. And oh, and while you should not go back to the notebook during the hack session, if you, in a week or something, go back and want to finish some of the examples or problems and you have questions, feel free to Slack message me. I'm happy to chat about it if you get stuck. Okay, so we already alluded to the topic of this morning, hierarchical models, yesterday in the last graphical model that we looked at. But today we're going to dig in a bit more. So as I started talking about yesterday when we were looking at that final graphical model, most of the models, the probabilistic models that you've looked at so far have been what I would call one-level models. And in these cases, they have structure that very generally looks like this. You have data that's generated one level up by some set of parameters that are maybe plugged into a functional model that generates the data. And so the joint distribution over the data and the parameters of some model can be factorized into a likelihood and a prior. You can factorize it the other way, get something that's the posterior and the evidence, and then you probably thought Bayes' theorem and Bayes' rule earlier this week. Now, hierarchical models, I think I also mentioned this yesterday, are sometimes called multi-level models because they can have multiple levels of hierarchy, meaning that random variables like parameters that you have can be related to other parameters that are higher up in the chain. And so, and that can keep going. So this is an example of having one new level of parameters. So there's this, again, reminding you this edge here means that there's a stochastic relationship between these things, meaning that there's a distribution involved, a probability distribution involved. This is not just a function, not saying theta equals alpha plus 2. This is saying that theta and alpha are parts of a distribution, like a Gaussian or a beta distribution or something like that. When you have, by the way, and this can keep going, because we'll see another example of that in a little while, but you could have another node up here that points to alpha, and then alpha points to theta, etc. And you can have the node up here point to both alpha and theta. So there is more intricate structure that can be involved in these multi-level models. But right now, let's just think about this kind of one-track hierarchy. Yeah.
So that means that D and alpha are connected.
D is only related to alpha through theta in this case. So, good. So let's look at the joint distribution over everything that's in this graphical model. D theta alpha, D theta alpha. So again, if you remember that arcane sentence I said yesterday, that looking at a graphical model tells you how you can factorize the joint probability distribution over all the things in the model. The fact that there's no arrow from alpha to D means that when we factorize this joint, D is only conditional on theta, but then theta is conditional on alpha. And then there's nothing points at alpha, so there's no conditional in that distribution. If D depended on alpha, if there's an edge that went like that, then this would have to be theta comma alpha here. And you actually wouldn't be able to factorize this, I don't think. Does that make sense? Any questions about this? Cool. So we're going to start right off the bat. We're not going to break out, but maybe just work individually for this one. We're going to do something collaborative in a minute. Think about how you write down the factorized probability distribution for this hierarchical model. So remember that one thing you might want to start with is by writing the joint. So the joint distribution is the probability of all the variables and data that you have in your model. So that's going to be all five of these symbols. And then do an equal sign and start thinking about how you factorize that thing, meaning write a bunch of conditional distributions that can be multiplied. And remember that this graphical model tells you how that can be done. you want to use the whiteboard, you can that way. Got it. Okay. How are people feeling about their factorized probability distribution? Marcus is feeling good. Sabine is feeling excellent. 2 thumbs. Does anyone have the urge to come up and write on the board? All right. Is it Messick? Where do I put the emphasis? Messick. Maybe here, I'll just raise the board a little bit. Here, that's probably a good one. Well, I say that. If not. Oh, and yeah. Here. You know what? I'm just going to leave it protected. Data, great. Data, Computational, alpha, and gamma, good. Alpha, Computational, data, and then we write required. Looks perfect. Cool. Nice job. Everyone agree? Oh yeah. I can do. You guys are. You're all like clapping. Not used to clapping. But yeah, good. Clap. Any questions about that? Yeah.
What's the difference between the data conditional on alpha and gamma versus like conditional on alpha and separately conditional on gamma?
You mean writing?
Yeah.
Okay. Is this equivalent to PU? That's the question. Anyone have a feeling? Remember yesterday I made that comment about units. So let's think about integrating this thing over d theta. And what about this thing? It actually means that this thing is just invalid. It doesn't have the right units because you have 1 over theta and 1 over theta multiplied by one another. So it doesn't tell you that you should do d theta squared. It just tells you that this is not good. Whereas this thing has units of 1 over theta times theta, and so this integrates to a dimension less. Cool. Good question, though. All right. Nope. Any other questions about this, by the way? Cool. Okay, so one class of hierarchical models that you'll see a lot, and maybe have even encountered already, are things called population models. And this is fairly common, I would say, in astronomy, where you observe some data for a bunch of objects, and then you want to infer the properties of the population of true objects based on observations that are one step separated from the population level parameters. So using the very general terms that we said before, by the way, I think I forgot to say the word. Yes, I forgot to say a word. Here in this structure, which we're going to come right back to, this is data. You might call these parameters. Sometimes the things that are one level up or several levels up are called hyperparameters. And so this thing, which has no edges pointing into it, will have a prior, the alpha. And to distinguish it now from this distribution, which in the one level case was a prior, this is sometimes called the hyperprior, which sounds very fancy in sci-fi, but it just means that you're an extra level up. The other comment I wanted to make here is that once you go to hierarchical models and in population models, which we'll see in a second, a lot of times what is likelihood and what is prior, that distinction can get blurred. And it's not as simple as it is in the case when you have a one-level model and there's a clear separation of this distribution. Like this thing is formally a prior, but maybe the data connects to other data over here or something, in which case the distinction gets a little blurred. Yeah.
I think we'll probably talk about this later, but if we go back to the other model.
This one.
One we just worked on.
This one, yeah.
I have two questions. Like how high up, how big a hierarchy before you start to get like ridiculous, you can't trust your results?
Raise your hand if you've ever seen a neural network or worked with a neural network. See, this blows my mind. So many of you raise your hands, but yeah, anyway. So neural networks you may have heard of the word layers. Neural networks have layers. You can write graph representations of neural networks, and you can go arbitrarily high and you can connect them in arbitrarily complex ways.
Fair enough. Looking at this example, what do you need to consider, like if you have a big hierarchy coming from one end to theta,
yeah,
versus like one node just on the right, like you know that much more about gamma compared to alpha, especially you need to feed in something with alpha.
Good. I don't have super general or insightful things to say about that because this is too general to be very useful. But I will say that if you have structures like this, you have to have very, very strong priors on these things in order to draw any conclusions about these things typically, because you get a lot of freedom every time you connect to random variables through a distribution. Like that increases the complexity of the model. And so that just means that the information flow from B to beta is going to be weakened by all of the random relationships of these variables. So typically, you won't see models that are exactly like this. You might see cases where there's different types of data that might enter and give you other constraints on these things. A good example actually is the tangential velocity, distance, proper motion, parallax example from yesterday, where if you get better at doing that, that looks like that has a structure like this, where that's shaded. And it doesn't really matter, but the point is that this thing is getting information from two observables, and the prior on this is helping to sort of like helps the information flow in this space. So in cases where you have many levels like this, you often need to have other kinds of data that help the flow of your model, or you have to have very strong priors in between here. Cool. Back to population models. So notice this is the same thing that we're just looking at. I've just now drawn a box, a plate around the theta and the d. These are called population models because in this case, the theta is inside of the plate. So this means that there's theta for n objects. There's also theta for n objects, meaning your parameter space is quite big. Can be if n is big. But then those parameters are connected to some hyperparameters, alpha, which are outside of the plate that govern the full distribution of true parameters that then generate your data. So just to give you a couple examples, and we're not going to draw graphical models or go into too much detail for these, but just to name a few. So one example of a population model could be, actually we're going to do an example of this in a minute. If you have exoplanet or binary star data, so imagine you have a bunch of light curves for exoplanets, transits, or you have radial velocity curves for binary stars. So the data you have are just a raw time series for a bunch of objects. The thing you want to learn maybe is the eccentricity distribution or the period distribution of the true systems that you have in your sample. A along the way, to go from the raw light curve data to the distribution of eccentricities, somewhere you have to model the individual eccentricities and periods of each system and connect that to the population or the distribution of eccentricities. Does that make sense? I put some other examples on here just to talk about other domains. So another example could be measuring the velocity dispersion of a galaxy cluster. So you observe the radial velocities of a bunch of galaxies in a cluster, and you want to infer the dispersion, the line of sight velocity dispersion. So one thing you could do is infer the velocities of each galaxy individually and connect them to a model for the distribution of velocities to measure the mean and the dispersion. That would be a population model. It could be expressed as a population model. Any questions about those two? Maybe I won't read through. That's just another example. So related to those two things, we're going to think about an example here, which is kind of an extension of the model that we thought about yesterday, which was when we were given a parallax, we observe a parallax, and we want to infer the distance to that star or that object. Now we're going to think about observing a bunch of parallaxes. So now we have a bag of parallax measurements for a bunch of stars. And we think that they're all part of a star cluster. You can sub-star for galaxy if you want, if you're used to thinking about galaxies. And we want to know the mean distance to that star cluster and the line of sight size of that star cluster. So now, whereas before, the one-level model we had was just R points to parallax. Now we draw a plate around the distances and the parallaxes. And we have some population parameters already. It's just that these were fixed nodes. They were closed circles. Now these are random variables that we want to infer. So that's what makes this a population or a hierarchical model. What are we doing here? Oh yeah, I'm going to switch to a Jupyter notebook in a second, and we're going to actually start coding. But I wanted to start by, what did I want to do? Oh, right. We're going to write down an expression for the posterior PDF. Very important to always say PDF after posterior for reasons that I won't explain. These three things, this is a vector, by the way. So this is bold R. This is, remember yesterday I said sometimes I'm going to draw a set around the thing. Sometimes I'll be lazy and just call it a vector. This is just all of the individual true distances to all of the stars that are in our star cluster. So these are all the parameters that we have, and this is a vector, again, a bold symbol. This is all of the parallaxes we have. So this is the posterior PDF. Let's write an expression for the posterior PDF. Again, using this graphical model as a way of figuring out how you might have factorized the joint PDF into the terms that you need to extract the posterior PDF. So we're going to do that, and then we're going to switch to Jupyter. Yeah. It's probably not.
So, just to, the understanding correctly is that if R and parallax are connected to some like Gaussian distribution, and we want to infer R, like so we have like multiple R's, and we're gonna follow some other distribution.
Yep.
So it's like doesn't have to be Gaussian.
Sure. Yep. I don't know how to rephrase that. But I guess the question was a statement that was that if R, a comment, if R and the parallax are related through a distribution, R can also have its own intrinsic distribution.
Yeah,
and that's what makes this a population or a hierarchical model. Right. So at your desk, or if you want to go to the board, let's write down what the posterior PDF will be. Hint, there's going to be a product involved because of this plate here. So again, I would start by actually writing down the joint over everything. and then see how you would factorize it in order to get an expression for this thing. Good. So, Julian, would you mind drawing what you drew on the board? All right. No problem. Yesterday, I think I called the thing bar pi, and today I'm calling it omega. It's a very weird symbol, but those are what people call it. Omega because it's like has the hat from pi, but it's omega. If you go back and you look at, I know now I'm just talking, but if you look at older papers, that's not good. Older papers about parallaxes, they use pi for parallax, but people switched because to some people pi means a different thing, like a number. So it was a little confusing. You had expressions with parallax and 4 pi in them, like you didn't know it. Cool. Okay, let's talk through it. So here's the joint.
Yeah. Oh, sorry. I misread that.
Cool. Good. How do people feel about that thing? So let's talk through it. So what would you call the likelihood up here?
Well, I would call these the priors first,
Cool.
and then I would call this the likelihood,
Good.
and then this represents the data.
Good. Yeah. So that's the vector of all omegas, right?
Yeah.
Omegas. Good.
And
Great. So that's the evidence. So I think the way that you got to it is you wrote down the joint and then you divide it by the evidence. That's one way of getting to the posterior. Yeah. Good. Yeah, you're right. Yeah. I love that comment out of context too. You can probably just erase the evidence. A lot of times, these astronomers, so a lot of times this is a very weird thing, and it's hard to evaluate. So the reason is that the thing. So let's go back to general terms. You're probably used to seeing. I don't know why the projector shut off, by the way. You've seen this, and then you probably also learn that when you're doing MCMC, especially with metropolis tasting, you can do this. This is proportional to, and the reason is because when you're doing MCMC, it involves ratios of expressions like this, ratios of the posterior, and then this thing at different values of the parameters cancels out because there's no theta in here. And that is a very useful thing because the evidence is this. It's the integral of your likelihood weighted by your prior over your full parameter space. Any ideas on this picture?
especially when the screen gets all the way up.
Oh, okay. And this thing is often, not always, but often hard to evaluate, this integral. And so anyway, maybe I'm saying things that you already talked about the other day, but that is one of the reasons that MCMC is so useful, is that you don't have to worry about trying to evaluate integrals. So you're absolutely right. Italian. That you might actually instead do your proportional symbol and then just write the numerator here. Yeah. Okay.
I have a tiny question.
Sure.
Technically, the evidence is also a product of the T for each omega, right?
Yeah. In our case, it would be this thing. It would actually be the integral of the top here.
No, I mean the evidence itself, right, as it's written right now, it's technically also a product of P omega 1, P omega.
Oh, yeah, right. Yeah. We could have written it that way, but because that's right, because there's the vector symbol here, that's kind of implied in the. I think. Oh, I see. It's because I stepped on that. Oh, but I'm gonna destroy my back doing this.
We do the models 1 notebook.
Yes, so if you want to follow along on your laptop, you can open up Hierarchical Models 1. Is this big enough in terms of code, since you have it on your screen as well? Cool. Okay, so this is just the note about making sure that you have this version of PyMC installed. The first cell is just a bunch of imports. And then again, we can skip a bunch of stuff because this is just generating the graphical models and the examples that we've done so far. So you can actually skip down to example, the mean distance of a simulated star cluster. The first thing we're going to do here is generate some fake data. So in this case, we're going to work with simulated data. We're going to generate 256 parallaxes following a true Gaussian distribution in distance. And then we're going to implement the model to infer the mean distance given the parallax. So this, I'm doing some AstroPy unit stuff in here. You don't have to do this, but I left it in as a demonstration of how you can use that. So if you have questions about that, you can ask me later. But at the end of this cell, we end up with a table that contains, each row contains a parallax and a parallax uncertainty or a parallax error, both in units of milliarc seconds. Hide that, I'm taking up too much space. So if we want to just, the first thing I always do with when I'm handed data, simulated or not, is make some visualization of it. So in this case, we're just given parallaxes, so it's just a one-dimensional thing. So you could make a histogram of the parallaxes. That would be one way of visualizing it. Here, instead, I wanted to show the error bars. So I just plotted the index of the given row in that table. And then I plotted markers where the parallax is with little error bars given by the parallax error that we have. So we have, our big N is 256. We have measurements of parallax, omega, and we have uncertainty in parallax. This is the graphical model for the model that we're going to implement. So we have these things as we need in order to infer those other things. We wrote down on the board or on your notebook here what the joint distribution looks like and how that factorizes into the posterior here times the evidence. And then you can use the joint distribution divided by the evidence equals to the posterior PDF. I wanted to make one aside here before we dive in, which is that in some cases, when you have a model like this, you can actually analytically marginalize out the per object variable. Have you heard the word marginalize in probability context, not in other contexts, in which case it's not a good not a good word. In the case of probability, it's a good word. So we can also say integrate. So have you thought about integrating out a parameter or a set of parameters that came up? Give me some more nods to make sure everyone saw that. Okay. So as we saw in a population model, you end up with often many parameters. Like in this case, if we have 256 stars, we're going to have 256 distances, which are parameters, unknown parameters. Many optimizers or samplers will have trouble when you have that many parameters. And so it's often useful that when you're given a model like this to think, can I integrate out any of the parameters that are there? Can I marginalize over any of the parameters that are there? If the relationship between distance and parallax was linear, we could do that marginalization here. We could do that integral. That integral would be closed form. That integral looks like this. You take the posterior PDF and you integrate over dr. In this case, this would actually end up being a product. So inside, it would just be a single integral. But as I just mentioned, in our case, we can't do this because parallax is 1 over r. So the integral is actually much harder to do than it would if parallax was equal to like AR plus B, for example. We would be able to do that integral in closed form analytically. So unfortunately, here we have to just suck it up and infer all of those 256 individual distances to get the population level parameters that we're actually after. And as I was just saying, many types of samplers like MC, maybe you've heard of, or optimizers like Powell or other ones that are in SciPy will have a very, very hard time generating good posterior samples or optimizing to a true optimum when you have that many parameters. The magic of many modern Markov chain Monte Carlo samplers, MCMC samplers, is that they can handle this many parameters. In fact, they can handle typically thousands, or even I've seen people use millions of parameters. And the reason they can do that is they use gradient information. And what I mean by that is they use information about the gradient of the likelihood, the derivative of the likelihood with respect to the parameters as a way of improving the efficiency of the sampling. Luckily, the whole reason we're doing this PyNC thing, that's all handled for you under the hood. You just have to write down the model, and under the hood, it figures out how to do all of the gradients and derivatives that it needs to do a very efficient sampling for you. You probably talked about that already. Maybe you talked about that already. Yes, okay, good. So I just wanted to reinforce those things and remind you why we're thinking about PyNC. Let's get on with it. So the population parameters that we have here are going to be the mean distance to the star cluster, or galaxy cluster, and the size of the star cluster along the line of sight. So this is written out in a lot of detail here that you shouldn't read right now, but I typically start in the opposite way that I read a graphical model. When I'm writing one down in PyNC, I tend to start thinking from top down. So I start with the population level parameters that I need for the next set of expressions that we'll see in a second. So the first thing we're going to do is define variables, PyNC distributions, to represent the population parameters that we have. So the first is the mean distance, mu sub r. So I'm going to use a truncated normal distribution. So that's just a normal distribution, has a mean and a variance or a standard deviation, but it's truncated at some value. And in this case, I truncated at 0. So the values can't go below 0. And the reason we do that, distances can't go below 0. So in this case, there's different ways you could do this, but I chose to just use a truncated normal. Truncated normal also means that this is a valid probability distribution. Even though we cut it at 0, it integrates to 1 from 0 to infinity. For the standard deviation, did you talk about Jeffreys priors or at all? Well, okay. So for standard deviations, I don't want to spend too much time on this right now, but let's talk about this later. It tends to be a good idea to use priors that look like this. And it turns out that one way of imposing this kind of prior and simultaneously enforcing non-negativity would be to define a new parameter, let's say A equals log sigma, and then sample with a prior on A that's uniform. So uniform in log sigma is equivalent to a prior that goes like 1 over sigma. So we're going to define a parameter that is the log standard deviation of R, but we're going to use a uniform distribution for that. So because we're sampling in the log of a value, that means it can't go negative because log is a discontinuity and you get man. And the uniform there on the log parameter gives us this prior. We can talk more about that in detail later. Okay, so those are our random variables. Now, we're sampling in the log standard deviation, but ultimately we need the standard deviation in order to plug it into our per object distribution. So instead of defining a new random variable, I'm going to define something called a deterministic, which is just a deterministic transformation of a random variable. So this doesn't define a new stochastic distribution. This is just saying I'm defining this variable standard deviation of R is the exponentiation of the log standard deviation. So that makes sense. Now we're just untransforming that variable. And now with that stuff, with the mu R and standard deviation of R, we can finally define a new distribution for all of the simulated data, for all of the rows in that table that we have, to get the true distances to each of those objects. Again, we're going to use truncated normal because these are distances, so they can't go below 0. Once we have that, now we're at that middle part of the graphical model. We've defined everything, these two things and this thing. Now we have to define the relationship between parallax and R. And we're assuming here that we have Gaussian uncertainties for the parallax. So it's one more Gaussian. Finally, normal, Gaussian, same thing. In this case, the parallax is 1 over these true distances. And now the key here is we have to pass in our data from that table that I showed you before. So we say this is observed at the parallax values, and the standard deviations are the uncertainties that we have. A lot. Let's see how PyMC would draw this graphical model. So note that it looks pretty similar to the one that we were looking at before. But besides writing the distribution names inside of the vertices, PyMC, when you do this, when you draw a graphical model, also tells you deterministic transformation. So in this case, this edge, because it says deterministic here, is not a new random variable relationship. It's just the transformation of the one that's up there. So with that in mind, this is exactly equivalent to what we had before. So let's try with that parallax model running the sampler. And here I've just set some initial values. So typically when you have a lot of parameters, it's good to think about initialization, where to start the initial guess when you're going to run the sampler. So for initial values, I just did a inverse variance weighted estimate of the distance of the cluster. And then I think I used that for all of the, true R values. Let's see how that sampler does. Hopefully you're running this under notebook. So I want to highlight how fast that was. 3 seconds it took to generate 12,000 samples for a model that has over 256 parameters. That really emphasizes the power of these probabilistic programming languages like PyMC. And again, this is all because the way that we've structured or defined the model is using this kind of weird notation where, like, if you printed standard deviation of R, it's not a Python value, it's this weird PyMC object. But the reason we do all of this is that under the hood, PyMC is actually building a graph of all of the mathematical operations that you've done for all of the variables you've defined, and it's figuring out how to take derivatives through that graph in order to very efficiently do the same thing. Yeah.
So for anything that have like kind of data points,
Yes.
they use time, this will beat out all the other like
Oh yeah. 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 In fact, yeah. Anyway, we can talk about that later. But you talked about metropolis tasting. Did you talk about other types of MCMC sampling methods a little bit? HMC. Okay, so this is HMC, right? Yeah.
And so actually, I noticed that the whole cell is executed in like 23 seconds, while actually the sampling is only 3 seconds. So do you know what's going on in the first 20 seconds during the initialization?
Do you really want to know? It's a little ugly. So the way that PyMC has to build that graph with all the mathematical operations is that it's actually constructing a bunch of C code and compiling it under the hood. And so this is what you don't want to go here, but because you asked, if you look in your .asara directory, you'll see things that say compiled here. So if we look in, say, this, all of these temps things are different PyMC models that I've compiled. And if we look inside one of these, like the one that we just did, probably this one. Notice that it's produced a SO, a shared object file, which is a compiled C library, essentially. So it's it's actually C++. It's actually hand building a bunch of C++ for you under the hood. So it's a scary thing, and when things go wrong, it can make it very difficult to figure out what the heck is going on. So I will say that is one issue with these kinds of probabilistic programming languages, is that debugging can be a little bit of a nightmare. On the other hand, the trade-off you get is we're sampling 258 parameters in 3 seconds, right? Like that's just an insane speed up. Cool. Okay, so you probably talked about this as well, but one question you might have after running this sampling, to remind you what we did, that sampling is generating sets of parameters sampled from the posterior PDF. So it's not telling us the posterior PDF, but it's drawing samples from it. That's what we end up with. We need to do something to assess, did this sampling succeed? Did the samples that were returned, do they look like they are good samples from the posterior PDF? The first thing I tend to do after running a sampler like this, especially if it didn't output a bunch of warnings, I'm a little surprised it didn't output a bunch of warnings, because it usually does, is I run something from RViz, which is another package that gets installed with PyMC, called RViz az.summary, and I pass in the samples. And that produces this nice table. Well, it looks nice to me. To you, it has a ton of like weird variable names that might mean nothing to you, but we're going to talk about some of them. But the first 2 columns are easy to understand. So the rows are the different parameters in your model. This is the mean value of the parameter, and this is the standard mean posterior estimate of the mean posterior value, and this is the standard deviation of the values of that parameter. So notice, we're nailing pretty precisely these parameter values here. So that's mean and standard deviation. HDI is, have you talked about credible regions at all? Okay, so we're going to skip that, but we could talk about that at another point. The final 3 columns are the ones that I tend to look at first, actually. I don't really care about the parameter values when I'm doing this. These give you a way of assessing whether the sampling actually succeeded and did a good job of drawing efficient samples from the posterior PDF. hat is the easiest because you just want it to be close to 1. And that's just like visually, you can just look, are the values close to 1? What R hat is, and this is the only one I'm going to expand in a little bit more detail, just so you know, R hat is known as a convergence statistic. Its full name, I think I wrote it down here, is the Gelman-Rubin convergence statistic, based on a paper by Andy Gelman and something Rubin, Rick Rubin, maybe. Sorry, that was a deep cut. The convergence statistic is basically a measure of if you run multiple independent sampling chains. So let's say we start from different initial values in some parameter of data, and we run random swaps like we did with MCMC. Is the variance between the chains similar to the variance within a chain? So yes, it's a measure of whether the variance between independent Markov chains is similar to the variance within an individual Markov chain. So the idea is you can't compute this if you only run one Markov chain, but something you might have noticed above is that PyMC doesn't do that by default. PyMC by default runs 4 chains. So that means it's starting from 4 different initial guesses and running MCMC forward using the model that you've constructed from those 4 different locations. And then at the end, it's computing, it's 4. Computing is the variance internal to a chain comparable to the variance between all 4 of those chains. Let that simmer, and we can talk about it more. So anyway, that's basically what I wanted to say, I think, about this. There's some other visualizations below. The first thing I do, though, is just look at this R hat number and make sure that it's close to 1. If it's close to 1, I then just keep going. And do something, for example, like make a corner plot, which is this. So you can use RViz to visualize projections of the posterior samples. So remember that what RViz, the sampling, the whole idea of sampling is you get points, you get samples from the posterior PDF. RViz then will project those and do a little density estimate using a kernel density estimator, and then give you something that looks smooth. But actually under the hood here are a bunch of individual points. So this is all of the projections of all of our parameters, so mu, standard deviation, and then just the first 3 true distances. So there would be, this corner plot, if I didn't truncate it, would be 258 by 258. It would be huge. So I just show you the first 3 true distances, 0, 1, 2. And the true values are the red markers. So it looks like, because this is simulated data, we know the truth. Looks like it did a pretty good job. Okay, so we're going to take a break now. But when we come back, we're going to break out into groups and work on a problem for the rest of the time. The problem is to infer the period distribution of low eccentricity binary star systems. We're going to work with real data from the apogee surveys. I've pre-selected out the data so that they're only low eccentricity stars, so the period distribution looks pretty simple. And there's, I think, 14 different systems, but 321 total radial velocity measurements distributed over this system. So we're going to implement a hierarchical model, and you're going to be sort of guided through how to load the data and visualize it and build up to the hierarchical model. But we're going to do that when we come back. So we're going to take a break. Happy to answer questions if you have any about the material before, and then we're going to do this when we come back. The samplers that you're using through PyMC. So some of you may have heard of MC. This is a Python package. It's an implementation of something called an affine invariant ensemble sampler. And if you remember back to Metropolis tasting, the way that it worked is you have some parameter space, theta 1, theta 2, and you have some posterior probability that you can evaluate, at least up to the constant evidence that looks like that. And you have to start with some point, and then you have to write down a proposal distribution, which is some distribution that you have to pick. You then, starting from an initial point, draw a sample from the proposal, and you accept or reject based on ratios of the posterior probability. And so then that's how you end up, doing some kind of random walk in space. And over time, you build up samples from the posterior PDF. That jog your memory, looks familiar. The way that, and similar, you can do a similar thing to talk about HMC, Hamiltonian Monte Carlo, which instead uses gradient information, gradients of the likelihood, and does Hamiltonian dynamics, which is actually really cool, but I won't talk about that for a sec. The way ensemble samplers work is pretty cool. So I just wanted to say one thing about that. So one of the disadvantages of Metropolis tasting is the fact that you have these tuning parameters which relate to how you do this proposal, that proposal step. And the efficiency of your sampling and the correlation that you have between steps in your chains, your Markov chains, depends strongly on how you set this proposal distribution. So the whole magic behind this ensemble sampler and the implementation in Python MC is that it removes that choice from you. So you no longer have to specify a proposal distribution. And the way that it works graphically is, again, you're in some parameter space, the same setup as before. Now, instead of starting from a single point, you start with some initialization of a bunch of points. So you now have to specify samples from some initial distribution. So that's the only thing that you have to set up. And the way that that MC works is you now want to evolve each of these points in parameter space. So you got to mark up an MCMC chain for each one of these points separately. And the way that you evolve each point, so let's say we want to evolve point 1 here. The way you do it is by randomly drawing from the bag of all other points. So we want to know where to take a step for this point. We randomly pick another point, let's say this one, and you draw a vector connecting the two, and there's a distribution that you use. There's a particular form of a one-dimensional distribution that you use to draw a sample along the line that connects those 2 points. So in this way, it's sort of adaptive in that you only have to set up this initial cloud of points in parameter space, and the thing then kind of morphs around in your parameter space, and you evolve or you step each of the chains using a randomly picked other point in your cloud. Another blocker is, I think, the terminology that Dan uses. The reason this is so cool is that it removes choices, so you don't have to now tune things, because this point cloud, if your posterior PDF has contours, density contours like this, even if you start with a big puffy cloud of initial points, it will actually adapt into something that samples this density pretty well. And it does that fairly quickly when your parameter space is small. So it's very efficient for 2 parameters, 4 parameters. At 10 parameters, already things start to get bad. And the reason is because the point cloud that you have has to fill the volume that you have in some way. It has to give you a good sampling of the density space that you have in the volume that you have. And as you might know, as you increase the number of axes, the volume grows quite fast, the volume of an object. So when you get up to 10 dimensions, you need a lot of these walkers in order to accurately map out the density distribution in a 10-dimensional space. At 200 parameters, forget it. You're not using MC. It's not going to work. It's never going to work. And so anyway, so that's why HMC and these Hamiltonian Monte Carlo samplers have been so impactful, is because they scale much better with the number of parameters that you have because they use the gradient information. Cool. Okay. So that was just an aside. Yeah.
Because for a lot of parameters, not a lot of data.
Correct. A lot of data is fine. Yeah. And in fact, another reason MC has been so influential, though, despite this bad scaling fact, is that in order to do this proposal, you just need to start with a cloud of points, and you need to have a function to evaluate the posterior probability. You don't need gradient information, and so you just have to write down a single function, log probability or log posterior probability, and you can run with this. Whereas for a long time, it was difficult to do HMC in practice because you had to write up log probability and then also code up a function that's the gradient of the log probability with respect to your parameters. And sometimes that's quite ugly. Sometimes you have a black box simulation or something that's running inside of your log posterior where you can't easily take derivatives through it. And so this is a great, this has been very influential for cases like that. Unfortunately, it just doesn't scale very well with numbers of parameters. So in modern times, I think most people would recommend using HMC methods. Okay. So we're now on to the problem, and I would recommend working in a pair, or at least maybe, talking to your neighbor. I sort of introduced it before we broke, but the idea is we have radial velocity measurements, add a bunch of time and uncertainties for those velocity measurements for 14 different sources. So they each have a different number of velocity measurements. And again, this is real data from the Apogee survey. I took known binary star systems from a paper a couple of years ago, and I just selected a low eccentricity system. I put them into this FIPS file here. So the structure of this file is just a big table where, so there's, I think 321 total rows, and it's ID, the name of the star, time, Julian date, velocity measurement, and uncertainty. So you can get out the unique number of IDs that are there using NumPy. And then this first cell here then just loops over all of those IDs, pulls out the data for a given ID, pulls out just the velocity data for that star, and then makes a plot of time, velocity with error bars. And notice you can basically not see any of the error bars because they're very small. So this is what the data looks like, velocity on the vertical axis and time in days on the horizontal axis. So you can see that there's variability there, definitely not single stars. And as the first step towards building up to the hierarchical model, and this is where I'm going to shut up, we're going to just start by fitting a model to a single star, one star's data. Then we're going to think about generalizing that to fitting all of the stars at the same time and connecting it to a hierarchical parameter. So now you're on your own. Raise your hand if you have any questions. There's a lot of text. Tried to explain things as best I could, but definitely ask questions if you have them. Sure. Actually then feed back down to the individual systems, the inferences you get for the individual systems. So in some cases, for example, inferring the true period distribution might improve your inference of the period of one of the systems in our sample, and that's called shrinkage. Whereas if you just asserted the prior, then it has none of the information about what the true population is underneath. It just has whatever your assumption was. So it gives you this opportunity to have information flow from from your better knowledge of what the true population is back down to the individual systems, which is powerful.
Can you repeat again what if you have an error greater than 1.5%?
Oh, just repeat what that means.
Yeah.
Sure. Yeah. So sometimes there's another plot function actually that I'm just going to show. I know we have one. We have 1 minute. Which is called plot trace. So I haven't executed this notebook. Okay, so you'll have to do this on your own laptops. If you do plot trace, that's going to make a plot that looks like it'll be, in this case, it'll be mu and on the sigma. So it'll be a plot that looks like 2 panels in this case, where the parameter value is on the vertical axis and step number on the horizontal axis. And if things went well, this will just look like a bunch of overlapping lines of different colors like this, centered on the true values, or the best values, I guess, the mode of the posterior. If things go badly, what it might look like instead, I can use the color. It might look like this. And what's happening in this particular case is that different initializations of the parameters, when you start to sample, are getting stuck in different modes of your posterior PDF. And so what that means, what's happening is that they're sampling pretty well inside of that mode, but between the different chains, the different initializations, there's a large variance, and they're not converged to the same posterior PDF mode. And so what R hat is looking at is the variance within one chain comparable to the variance estimated between all of the chains? And if there's a big discrepancy, R hat gets bigger. If they're comparable, like in the case of the black lines here, like the variance of one chain here is equivalent to the variance across the chain, then you have an R hat close to 1. I don't remember the exact definition, but that's the concept.
I'll also quickly add, if you are doing this type of analysis, it's always a very good idea to look at the chain. As a way to just know that you are converging in the way you expect. You can also see chains that jump from, so not just that are stuck in a mode, but jump from a mode, but that never gets back to where it started or things like that. Be a sign that.
Yeah, that's a really good point. Yeah, discontinuities in the trace plots are bad. Okay, I think it's time for a photo.
Yeah, so let's finish it one more time.